Now that we have the basic operations of matrices down, we need to do one more thing before we can get to what we really want to do, which is talk about solving matrix equations. We need to talk about the inverse of a square matrix, what it is, why it's important, and how to find it if it exists. So before we do that, a little bit of terminology. The identity matrix, usually denoted I or I sub n, or if you really want to sort of indicate what size it is, the identity matrix I sub n is an n by n matrix, so a square matrix, n rows, n columns, whose diagonal entries are all ones, and all of the other entries are all zeros. So for example, I2 is just this matrix, 2 by 2 matrix, 1, 0, 0, 1, right? So all of the entries on the diagonal are ones, everything else is 0. I3 is the 3 by 3 identity matrix, all of the entries on the diagonal are ones, everything else are all 0. I4, the 4 by 4 identity matrix, all of the entries on the diagonal are ones, everything else is 0, and so on, right? So in general, the n by n identity matrix has n rows, n columns, and it looks like this. Everything on the diagonal is 1, everything else is 0. And the identity matrix has a very important property. I'll illustrate it now. Something like, let's just take any old 2 by 2 matrix. 2, 3, minus 4, and 1. And we'll multiply it by I2. 1, 0, 0, 1. Multiplying by the 2 by 2 identity matrix on the right. What do we get? This is defined, 2 by 2 by 2 by 2 is no problem. And I'm going to do first row by first column. 2 times 1 is 2, plus 3 times 0 is 2. First row, second column, 2 times 0 is 0, plus 3 times 1 is 3. Then we've got minus 4 times 1 is minus 4, plus 1 times 0 is minus 4. And minus 4 times 0, plus 1 times 1 is 1. So what do you notice? I multiplied this matrix by I2, and the result is the exact same matrix that I started with. So in other words, multiplying by this identity matrix didn't actually do anything. It's sort of like when you multiply a real number by 1, it doesn't change the number at all. And this is why this is called the identity matrix, is because it's the multiplicative identity. It plays the role of 1. When you multiply the corresponding size matrix by it, it doesn't change the matrix at all. So, basic fact, if A is n by n, then multiplying A by the n by n identity matrix, I sub n, on either side, A times In, or In times A, is just A. This is why the identity matrix is important, because again, in real numbers, 1 is a very important number, and it's important because when you multiply by it, it doesn't do anything. This is sort of the matrix version of 1, right? So it's I sub n is the n by n matrix version of 1. When you multiply an n by n matrix by it, it doesn't change anything. You just get the original matrix out that you start with. Okay, so here's our definition for the multiplicative inverse of a square matrix. So let A be a square n by n matrix. This is important. We're only talking about square matrices now. So every single time I talk about a matrix, in this case it will be a square matrix, n by n in particular. If there exists another n by n matrix that I'm denoting A inverse, that has the following property, so when I take A by it, and I multiply by A inverse on the right, or I multiply A by A inverse on the left, I get out the n by n identity matrix In. So if such a matrix exists, then we call this matrix A inverse the inverse matrix of A. So what's happening here? What is this trying to get at? Well, suppose I took the real number 3, right? What is I sub n? I sub n is playing the role of 1 for matrices, right? It's like multiplying by the real number 1. So if I took the number 3 and I asked, what do you multiply 3 by? What do you multiply 3 by to make it equal to 1? Well, the answer is 1/3, right? And you can do it on either side. You can multiply 3 by 1/3 on the right or on the left, but in either case, you multiply 3 by 1/3 to get 1. What if I took pi? What do you multiply pi by to make it equal to 1? Well, you multiply by 1 over pi, right? But there's other notation we use here. Instead of writing 1/3, another way you could write that is as 3 to the minus 1, right? Or instead of 1 over pi, I could write that as pi to the minus 1. So these numbers, 1/3 and 1 over pi, these are the multiplicative inverses of 3 and pi respectively. They are the numbers that you have to multiply by to make them equal to 1. That's what we're doing up here with matrices. We don't have 1, but we have the matrix analog of 1, which is the n by n identity matrix. And the question is, what do I multiply A by to make it equal to 1, to the identity matrix? And if I can find such a matrix, we call it the identity matrix. What's the problem? Well, the problem is A inverse is not just 1 over A, because that doesn't make any sense, right? What does it mean to divide the number 1 by a matrix? That doesn't make any sense at all, so don't think of it in terms of that. It's just a matrix that has this property. When I multiply A by it, I get the identity matrix. Okay, so here's a 2 by 2 matrix. A is 3, 1, 2, 1. And we're asked to just verify that this other matrix, 1, minus 1, minus 2, and 3, is the inverse of A. So what does it mean to verify it? Well, I want to show that when I multiply them together, I get the 2 by 2 identity matrix. So A times A inverse, we'll compute it. 3, 1, 2, 1. Multiply this by 1, minus 1, minus 2, 3. I'm hoping to show that this comes out to the 2 by 2 identity matrix, 1, 0, 0, 1. So let's see what happens. Row 1, column 1, row 1 by column 1, 3 times 1 is 3, plus 1 times minus 2 is 3 minus 2 is 1, just like we wanted. Then we got 3 times minus 1 is minus 3, plus 3 is 0, just like we wanted. Now we're doing row 2 by column 1, 2 times 1 is 2, plus minus 2 is 0, just like we wanted. And last but not least, row 2 by column 2, 2 times minus 1 is minus 2, plus 3 is positive 1. Awesome. So we got what we wanted. You'll also have to check this. You'll also have to check that, but I'll leave it to you. I'll leave it to you to compute this, and I promise you it will come out to this. So, turns out this guy is the multiplicative inverse of the original matrix A. The question then is, if I give you a matrix, how do you find the inverse? The answer is, it's not that easy. It is kind of easy in the 2 by 2 case. I'll give you a little shortcut right now. I'll tell you how to compute for the 2 by 2 case. So for 2 by 2 matrices, there's a fairly simple formula for finding the inverse. So if A is this 2 by 2 matrix A, B, C, D, then A inverse is the scalar product 1 over AD minus BC times this 2 by 2 matrix D minus B minus C A. So I've flipped the two diagonal matrices here, or the two diagonal entries I should say, A and B are flipped, and the other two sort of non-diagonal entries are multiplied by minus 1. And then you multiply the whole thing by this scalar 1 over AD minus BC. I want to point out there's a catch. Notice that AD minus BC, that can be 0, right? That number can be 0, and this gives me 1 over 0. And that doesn't make any sense. So in that one particular case where AD minus BC is 0, an inverse simply doesn't exist. So note, if AD minus BC equals 0, then A inverse does not exist. And this is interesting. This is sort of unlike real numbers, where multiplicative inverses for lots of matrices out there, they just don't have to exist. There is no A inverse. So, and for 2 by 2 matrices, this is precisely when this happens, when this product AD minus BC is 0. So in that case, the matrix inverse doesn't exist, and we have a name for matrices like these. I tend to just call them non-invertible matrices, but the formal name would be singular matrices. So we say A is non-invertible, or the very fancy word, singular. So that can happen, but otherwise, for 2 by 2 matrices, finding the inverse is just using this simple formula. So, for example, let's see here. Find A inverse if A is 2, 4, minus 1, 1. Okay, well, we'll use our simple formula. A inverse is going to be 1 over AD, 2 times 1 is 2, minus BC, minus 4 times minus 1, minus 4. So that's non-zero, that's good. Times, we flip the two diagonal entries, so this becomes 1, 2, and the other two multiply by minus 1, so minus 4, and minus 1 times minus 1 is positive 1. So what's that? This is 1 over 6, so we're multiplying all of the entries by 1 over 6. So we've got 1 over 6, minus 4 over 6, which I'll simplify, that's minus 2/3. Here we've got 1 over 6 again, and here we've got 2 over 6, which I'll simplify, is 1/3. And I'm running out of space, but I would urge you now to check this. Check that when you multiply A, this original matrix, by this one, on either side, that you get the 2 by 2 identity matrix, 1, 0, 0, 1. So I leave this to you, but check that it actually works as an inverse. And let's just do one more. So find A inverse if A is 2, 6, 1, 3. Okay, so same thing. We'll compute A inverse is going to be 1 over AD minus BC. 2 times 3 is 6, minus 6 times 1 is 6. Oh, wait. Well, that gives me division by 0, right? AD minus BC was 0. So that means that an inverse, A inverse, does not exist. Which can happen, right? Inverses for matrices don't always have to exist. So 2 by 2 matrices have this nice shortcut, this nice formula for finding the inverse. Unfortunately, nice formulas like this don't exist for bigger square matrices, 3 by 3, 4 by 4, and so on. But there is still a fairly nice algorithm for how to find the inverse. It's much more involved, it involves Gauss-Jordan elimination, but I'll give it to you now. So a rather simple algorithm for finding the inverse of a general n by n matrix A. And all we have to do is build this object here, build the augmented matrix A and IN. What I mean by this is I've got a matrix where I put this whole matrix in here. I put the whole n by n matrix A in here. I put an augmentation bar, and on the other side of the augmentation bar I put the whole n by n identity matrix. And then we start row reducing it. And if, when you put it in reduced form, it looks like this, it looks like the n by n identity matrix to the left of the augmentation bar, and then some stuff to the right, some matrix B to the right, well then that matrix B is the inverse of A. And if not, if you can't do this, when you put it in reduced form, you don't end up with the n by n identity matrix over here. Maybe you have a row of all zeros or something. So you put it in reduced form and it doesn't look like that, then A is not invertible. It's a singular matrix and no inverse exists. So that's the whole algorithm. I'll do just one example. If you want to see more, there's more in the textbook, but it's the same algorithm every time. So I'll just do one example with a 3 by 3. Okay, so here's our last example. We're given a 3 by 3 matrix, and we're asked to find the inverse of A, which is this 3 by 3 square matrix. Remember, it has to be square to even have an inverse. It's a 3 by 3 matrix: 1, 2, minus 1, minus 4, minus 7, 3, minus 2, minus 6, 5. Find the inverse if it exists. Of course, not all matrices have inverses, but we'll take a look at this one, and we'll follow our algorithm. So first thing we'll do is we'll build this, this matrix A and I3. Why I3? Why the 3 by 3 identity matrix? Well, because it's a 3 by 3 matrix we're working with. So we'll build this thing. We've got 1, 2, minus 1, minus 4, minus 7, 3, minus 2, minus 6, 5, augmentation bar, and to the right of this augmentation bar, I'm going to put the matrix I3, so 1, 0, 0, 0, 1, 0, 0, 0, 1. This bar is just a notational device. Formally, this is a 3 by 6 matrix. And what do I want to do? I want to row reduce this. I want to row reduce this down to its reduced form, and hopefully we'll end up with the identity matrix over here to the left of the bar. So what do I do? Well, first things first, I want to put a non-zero entry here that I'm going to use to zero out everything below it. And a 1 would be ideal. We already have a 1 right there, so I'm just going to leave that alone. And I'm going to use this entry to zero out everything below it. So I want to add 4 times row 1 to row 2, and 2 times row 1 to row 3 to put zeros here. So we'll do row 2 plus 4 times row 1. We'll replace row 2, and row 3 plus 2 times row 1 will replace row 3. So row 1 is going to stay the same. I'll keep row 1 exactly the same. And now let's carry out these operations. Row 2 plus 4 times row 1. Minus 4 plus 4 is 0, just as I wanted. Minus 7 plus 4 times 2, minus 7 plus 8 is positive 1. And 3 plus minus 2 is positive 1. Don't stop there. Keep going. Remember, this is just a bar. It's just a notational device. We keep going across the entire row. So now I've got 0 plus 4 times 1 is positive 4. 1 plus 4 times 0 is 1. 0 plus 0 is 0. Okay, so continue on down the whole row. And over here, we're now doing row 3 plus 2 times row 1. So minus 2 plus 2 times 1 is 0, just as I wanted. Minus 6 plus 4 is minus 2. 5 plus minus, what do I have? 5 plus 2 times minus 1 is 5 plus minus 2 is 3. I've got 0 plus 2 times 1 is 2. 0 plus 0 is 0. And 1 plus 0 is 1. It's very, very easy when you're going through this because there's so many steps, so many times I'm doing this basic arithmetic. It's very easy to make mistakes. Not just the copying errors that you have to look at because you're copying stuff so many times, but just simple arithmetic mistakes. I'm going to check this against my notes very quickly. It looks like I made a mistake. Yeah, I'm going to check this against my notes quickly, and you'll see that I did make a mistake. My notes say I should have a minus 1 right here. What went wrong? We have a 3 plus minus 4 times, or sorry, 3 plus 4 times minus 1 should be 3 minus 4. That should be minus 1. Glad we caught that. Again, because if we didn't, this error would have carried all the way through and we would have eventually ended up having to restart the whole thing. So we'll keep going. What now? Well, now remember the Gauss-Jordan elimination, the algorithm. We've zeroed out everything below this leading 1. Now we mentally cross off that row and we repeat the process. So now I want to put a non-zero entry here that I'm going to use to zero out everything below it. A 1 would be ideal. I already have a 1. So I'm just going to use that to zero out this entry below it. So how do I do that? Well, add twice the second row to the third row. So we'll do row 3 plus 2 times row 2 will become our new row 3. I'm going to have to write a little bit small to squeeze this in here, but it should be okay. Let's see, row 1 stays the same. I'm going to be careful not to make copying errors as we copy it down. 1, 2, minus 1, 1, 0, 0. Row 2 stays the same. and row 3. Okay, what are we doing? We're doing row 3 plus 2 times row 2. So 0 plus 0 is 0. Minus 2 plus 2 times 1 is 0, just as I wanted. 3 plus 2 times minus 1, 3 plus minus 2 is positive 1. Remember, don't stop at the augmentation bar, continue down the entire row. Here I have 2 plus 2 times 4, 2 plus 8 is 10. 0 plus 2 times 1 is 2. 1 plus 2 times 0 is 1. Once again, check my notes very quickly. Looks like we're fine. Now what? Okay, so we cross off mentally the first 2 rows. Well, we're down to our last row. There's nothing else to do. So what do we do now? Well, now we rescale this. If it's not a 1, we rescale it to a 1, which it is. And then we use that to zero out everything above it. So how am I going to do that? Well, I'm just going to add row 3 to row 2 and add row 3 to row 1 to put zeros here. So we'll do row 1 plus row 3 will become our new row 1, and row 2 plus row 3 will become our new row 2. Alright, so 1 plus 0 is 1, 2 plus 0 is 2, minus 1 plus 1 is 0, just as I wanted. Then I've got 1 plus 10 is 11, 0 plus 2 is 2, 0 plus 1 is 1. And row 2 we're doing the same thing, we're adding row 3 to row 2, so 0, 1 plus 0 is 1, minus 1 plus 1 is 0. 4 plus 10 is 14, 1 plus 2 is 3, 0 plus 1 is 1. And row 3 stays exactly the same, so. Looks okay so far. Now there's actually only one more step we have to do. There's only one more step we have to do, which is come to this leading entry. Rescale if it's not a 1. It is a 1, so no rescaling to do there. And use that to zero out everything above it. So I need to zero out that 2, which means I'm going to be subtracting 2 times row 2 from row 1. So row 1 minus 2 times row 2 will become our new row 1. Let's just copy down row 2 and row 3 since we're not going to mess with them at all. And okay, so we're subtracting 2 times row 2 from row 1. 1 minus 2 times 0, 1. 2 minus 2 times 1, 0, just as I wanted. 0 times 2, minus 2 times 0 is 0. 11 minus 2 times 14, that's 11 minus 28 is negative 17. And 2 minus 2 times 3, 2 minus 6 is minus 4. And 1 minus 2 times 1 is negative 1. Mission accomplished. We were able to put this in reduced form. This is now in reduced form. This is a reduced row echelon form. We have I3 over here, 3 by 3 identity matrix. If it was in reduced form and I didn't have I3, say I had a row of all zeros, this matrix would not be invertible. It would be a singular matrix, and we would just say no inverse exists. But because we have I3, an inverse does exist, and this matrix right here, that is our inverse. So A inverse is minus 17, minus 4, minus 1, 14, 3, 1, 10, 2, 1. And that's the process. That's the algorithm. You can check this. Go ahead and multiply A by A inverse on the left and the right, and you'll find that the product is indeed the 3 by 3 identity matrix, so this is the inverse. You can check that. But that is the algorithm. It's sort of, it's an involved process, it's lengthy, it takes a little bit of work, but it is just Gauss-Jordan elimination, which hopefully we're good at by now. So this is the only one I'll do. This is the only example I'll do because they take so long. But the algorithm is the same every time. If you want to see another example, the textbook does another example, but 3 by 3. But we'll stop here.